Today's math lesson for 8th grade has to do with surface area and volume. The reason for combining these two concepts is because they both apply to a three-dimensional figure. This particular box, for example, has both surface area and volume. What's important, however, is that the amount of surface area, in this case, the sum of the areas of the faces or surfaces of a three-dimensional figure, also referring to the amount of material needed to cover an object if you were going to wrap it like a gift, or the amount of material needed to create the container, is the same whether it is in its three-dimensional form or in its flat two-dimensional form. The amount of surface area is the same. However, it only has volume when it's in its three-dimensional form. That is when it has the capacity to hold, because volume is the number of cubic units needed to fill a given container or three-dimensional space. You are literally filling it up. It could be asked in a number of ways, including how much a container can hold, how much will fit in a container, or how much it takes to fill a container. Frequently, items such as sandboxes and swimming pools are used for these type of questions. Another distinction is the units. Surface area is measured in square units, just like regular area. We are literally talking about how many little squares, square units of area are comprising that particular figure, whether it's in its three-dimensional form or in its flat two-dimensional form. When we're talking about volume, however, we're talking about cubic units, literally the number of cubes needed to fill up a given container. Knowing those particular units can help you when you're trying to narrow down or figure out what a question might be asking you, and it doesn't come right out and say surface area or come right out and say volume. Okay? The figure that is being used for demonstration is the triangular prism because it's the one that most students have trouble with. Their interpretation of the figure sometimes gives them difficulty when they are trying to find surface area, particularly if they prefer the method where they can lay the figure out flat and find the individual areas and use those numbers to find the total or lateral surface area. However, sometimes this two-dimensional version, also known as a net, isn't available and students have to create their own. The ability to go from the 3D to the 2D correctly challenges many students. So what I like about this particular example is that it shows the 5 in 2 places, indicating that this side of the triangle attaches to that rectangle. This distance of 4 is equal to this distance of 4 because this side of the triangle connects to this rectangle. This side of the triangle is already attached to the third rectangle. So each one of those rectangles serves a purpose of closing off one of the 3 sides of the figure of the triangular base. That is why if students understand that each one of those rectangles is doing that, then finding the correct rectangular size comes solely from the sides of the triangle. If your sides are 3, 4, and 5, therefore you need one rectangle that is 3, one rectangle that is 4, and one rectangle that is 5 to close it off. That generally leads to more success in trying to draw the net if it is not provided for you. Okay, if you were going to find surface area by what we call piece method, that is finding each individual portion of the figure and adding them together as appropriate, that is fine, but you need to understand that not all areas come simply from multiplying. Yes, areas of these 3 rectangles are simply base times height, base times height, base times height. Length times width is another way to look at it. Triangles, however, are different. We do want the 2 sides of the triangle that give us the right angle. Those are the 2 that are used in the area of a triangle formula. Therefore, a half of 12 is 6 square centimeters. That means that this triangle has an area of 6 square centimeters, and this triangle has an area of 6 square centimeters. This rectangle is 4 by 7, meaning it has 28 square centimeters of area. This is 3 by 7, 21 square centimeters of area. And 5 by 7, 35 centimeters squared, or square centimeters of area. Now, What pieces we use depends on what we're being asked. There is lateral, which means without the bases. This is an example with a rectangular prism. Without the bases means it's hollow, you can see through it. With the bases is your total. Same thing here. We have the triangular prism, all the pieces. Here, the two bases are missing. It's hollow, that is lateral. If you're talking about something like a cylinder, we are talking about the tube only for lateral, no bases, or a container that has both a top and a bottom, total surface area. So if we wanted lateral first, we would only be using the three pieces that make up the rectangular portion, because lateral means without the bases, we would not be using the 2 sixths initially. 28, 21, and 35, 84 centimeters squared. That is our lateral. To take it the rest of the way to total, we would simply add in our two bases, taking us to 96 centimeters squared. Lateral without the bases, total with the bases. You can also use the formulas that are on the math chart, but you must know the meaning of capital P and the meaning of capital B. You cannot do this using the formulas on the chart unless you understand the meanings of those two variables, and they are not explained for you. P does happen to be the perimeter of the base. 3, 4, and 5 are the sides of the triangle. That is a total of 12 feet times the height, in this case 7. I know many students look at that and say, how can that be the height? It's because the triangular prism is not sitting on its base. However, if we were to stand up on this triangular base, then that height is more obvious as being a vertical measurement. So 12 times 7 gives us the same 84. It just happens to be feet in this circumstance instead of centimeters like it was here. Same number regardless of method. Here we've already done this piece. We just did it. 84 plus 2 times the area of the base. Those are our triangles. We've already calculated that. Again, 84 plus 12 does give us 96. The same number, just happens to be feet here, that we got using the other method. So regardless of method, you can be successful. Volume is actually quite easy. It's just area of the base times the height. We'd already found the area of the base, and we know our height is 7. Therefore, our volume is 42 cubic centimeters. In this case, it would be cubic feet. In this case, again, surface area, square units, volume, cubic units. All right. Now, what you need to be aware of, particularly with triangular prisms, is that sometimes there's a number missing. Here, you do not know the vertical height of the triangle. You cannot find the area of the base without it. Therefore, you would need to use Pythagorean theorem. Knowing C, you already know C, it would be actually the leg, A or B, that you would be looking for. Here, you know the two legs of the triangle, but you would need Pythagorean to find that missing side also in order to be able to find surface area or volume, at least surface area depending on method that you do. Same thing here, you would have to find this third side of the triangle. However, what you need to be aware of is that you're not using the entire 8, but only half of that base, because it's a Pythagorean is a triangular right triangle concept. All right. If you're working with a rectangular prism, most students have little difficulty laying that out flat if they find that useful. Cylinders, they don't really need to be laid out flat because the formulas are very user-friendly. Nothing you haven't used previously, as long as you know the difference between radius and diameter. This is the diameter that's being shown, but radius is what's in the formula. As long as you substitute correctly, you should have no trouble. Same thing with Volume of a cylinder, you just need to understand that capital B is area of the base, and in this case, that's area of a square. A equals pi r squared. Some other situations you can find yourself in, particularly with volume, are some variations. Not just one figure, but perhaps a figure inside a figure on top of a figure, or a partial figure on top of a figure, all of which give you extra challenges. But if you know how to find volumes of individual pieces, you should have no trouble tackling any of these challenges put before you. That concludes our lesson for today. Hope you have learned something, and good luck on the quiz Thursday for whoever's competing from your homeroom.